and we'll get started here. So we're going to continue on with more free radical reactions. We'll talk a little bit about stereochemistry of the free radical reactions. And then basically we're going to add the two most free radical mechanisms follow something pretty close to what we talked about for the halogenation, where it pulls the hydrogen off and replaces it with a halogen. The allylic bromination and that anti-Markovnikov hydrobromination, they both have very slightly different mechanisms, and there's some other variables we need to consider. Because it turns out these two kind of compete with each other, and if we're not careful about reaction concentrations, we actually don't get great yield on either of them. So we're going to look at some of the wrinkles that go into kind of trying to maximize one versus the other. And I spent a lot of time last night and today and this morning trying to convince myself why the concentrations work to control the way that they do. And I'm still not entirely sure that I believe them. So I think you're always going to get those competitive mechanisms like we've talked about before. Everything that can happen does happen. So it's more about, we're going to pretend like the other one isn't happening for the sake of writing the major product in most of these cases. And there's a couple key indicators that'll tell us which of these routes are we going. But for starters, let's review the one we did last time. Let me fix that. So let's look at this reaction here. I'm putting it down to where we can see that. So if we've got this molecule here, and I didn't specify when I drew this molecule, but let's assume that we're starting with this stereoisomer. This methyl's coming out of the board. So first off, what's the major product we're going to see? So bromination, remember, favors very heavily. Are we looking for what the most hydrogens, or are we looking for the most stable hydrogen pull-off?
Just the most hydrogens.
That was a chlorination.
Oh, sorry.
Chlorine is the more reactive one, right? So for bromine is a little less reactive. And so it's really a lot more about finding the easiest hydrogen pull off, not the most hydrogens. And the way that you can remember that how reactive they are is, one, we don't use fluorine because it blows up. Chlorine is in between, it follows that trend down the periodic table. Fluorine is super reactive. Chlorine is very reactive and not as bad. Bromine is sort of the sweet spot, and iodine is not reactive enough. And in terms of everyday life, you use chlorine in pools and bromine in spas because of the temperature difference. Because the chlorine would be too reactive at hot tub temperatures compared to bromine, and bromine wouldn't be reactive enough at pool temperatures. So that's one way to remember it in terms of everyday life. So which of the hydrogens is going to be the easiest to pull off, have the lowest bond association energy? Yeah, the tertiary carbon. Quaternary doesn't have hydrogen. The rest of these are secondary or primary. So we're looking to pull off that hydrogen there. So our product is going to be putting a bromine on this carbon. Are we going to favor a specific stereoisomer? Why not, David?
Because the intermediate is basically sp2 with it being the radical.
Bingo. Yeah, because we're make that radical intermediate. Our intermediate, and we'll see it when we draw the mechanism here in a second, but our intermediate is going to be this molecule, which is gonna be planar. So it doesn't matter which, or it doesn't matter that we started with the methyl group facing up because our intermediate is planar, which means the bromine that it then is going to attack. So remember, we're not drawing these are not nucleophilic attacks. These are free radical attacks, so they always look a little bit different. Yeah, something like that, and it doesn't matter whether that bromine is on top or bottom. We're gonna get an even combination of both. No, so we'll draw the whole thing. Let's start with the initiation. What would the initiation step look like for this mechanism? Thanks for the setup, the segue. I did, yeah. So what does the initiation look like?
The bromines split,
Bromine splits. And how do we draw those arrows?
single bar, each row.
Single barbed arrow, one each direction. Technically, and when we're drawing this arrow here, we would show that with the light. It's really the light that causes this, right? So it seems weird with the light after we actually drew the arrows, but that's just a common way of drawing it. The other way that you can show it if you want to be more explicit is you can write your H nu like that and draw it as a wavy arrow, as a literal wave arrow. Hitting that bond, that's what you show light, a photon hitting a specific bond. This is good enough, but that fits my OCD need to go left to right a little bit better.
More into.
I would think so too, but I try not to post that on others. All right, so then the product of the initiation step is just going to be 2 bromine radicals. Easy enough, right? Some of the mechanisms that we're going to look at that we're going to add, the allylic bromination and the anti-Markovnikov addition, actually have more than one initiation step technically. But for most cases, we're going to have one initiation step, and then it's going to be multiple propagations and then a single termination. And really, you only ever, like we talked about on Tuesday, there's any number of possible termination steps you could draw. We're basically just going to pick one, and it doesn't really matter which one you pick. By convention, we pick the one that gives us our final product, but it doesn't make that big of a difference. So what are our propagation steps then? Remember, what are our keys to know how many what propagation steps we should be drawing? How do we know if we drew the propagation steps properly?
Oh, if you cancel out the free radicals.
If we cancel out the free radicals to just get our net reaction. So we've got a bromine radical that's going to be part of this first part, or this propagation step. I guess it can be helpful to fill in the complete product or the complete reaction here, right? It's really Br2 as a reactant. And what's our other product? We get this organic product, but then also hydrobromic acid. But filling that in helps with the propagation steps because we don't need to make this in our first propagation step. We can make this. So what would that look like? What's our other reactant we're going to draw? Part of the reactant. In this case, since we're doing a hydrogen abstraction, we probably want to draw the hydrogen out, right? Then, just like we saw here, fish hook, single barbed arrows. It can be hard to make sure you give yourself enough space when you're trying to draw everything. So sometimes it's actually, it can be helpful to just overemphasize that arrow. especially since you're not working with a whole whiteboard on your binding paper. So that gives us HBr. And then our radical intermediate, the one that we already drew over here. Which again is not truly SP2, but because that hydrogen radical is higher in energy, you're not going to mix it in with the SP to make it look SP3. Right, so a carbanion. So if we had actually, if we had a methyl carbanion, we wind up with a lone pair on the carbon there. That gives it the negative charge, right? This is still going to be sp3 because it's still a full valence on that carbon, right? If it's still full valence on the carbon, all of those hydrogen, all of those orbitals have to be mixed together and give you the 4 bonding groups. And that puts 3 of your 4. Remember, we're really mixing 2s orbital with the 2p orbital, and we're mixing all 4 of these together to get 4 orbitals that are somewhere in the middle, right? The fact that we have a free radical in one of those instead of a double pair of electrons means that actually puts one of these sort of even higher in energy because it's close to being filled. Right, and so basically what we do is we don't mix that one in because it's so high energy. It's no longer favorable to let that one hybridize. Not like the carbon has anything to say consciously about that, but mathematically, that one doesn't get included because that would make everything else too high in energy. So it still hybridizes the 2 of the p pieces, and it mixes in the s orbital, but it's not going to include that third piece of a p orbital. Thank you. Because it's a free radical, and that allows it to behave more like it's sp2. Even though it doesn't really make sense for it to be sp2 because it has an electron. That's why it does make sense. It all comes back to Linus Pauling and hybridization. Good old Pauling. Did I mention to you guys that we had his great niece, Linus Pauling's great niece, was in one of our chemistry classes here. She took the OChem sequence or the Gen Chem sequence here.
Seriously?
Yeah. And then she came back, she did conservation biology was her major, and she went off to Africa to work in conservation biology, and she came back to speak to students about it too. She was fun to have in class because she would actually tell like personal stories about Linus Pauling, which, I mean, that's like meeting Neil Young. All right, so what's our second propagation step going to look like here? If I left myself enough room, normally I would keep them together so we can see them adding up. I'm going to use the space over here. Well,
More diatomic bromine.
more diatomic bromine. We haven't in our propagation steps, we haven't used this as a reactant yet, right?
Yeah.
And we also haven't shown our final product yet. So we know that our second propagation step is going to have diatomic bromine on the reactant side. We're going to want this one to cancel out, so we're going to put this one on the reactant side as well. And we know where we have to make our final organic product. And this is what's going to be going to allow us to cancel out the bromine radical here. We know we have to make another bromine radical as well. Make that look, make sure that doesn't look just like our initiation step.
Do we have to include this splitting with bromine because the bromine?
We do, because this is what keeps it going. If we just were showing, using the second bromine radical here, then that's not really propagation because we'd be using up all of our bromine radicals.
And basically, if like we start with some light and we take the light away and keep going because of that, so that's what we show that.
Exactly.
Uh,
Which is what makes it propagation and not initiation in the first place. All right, what's the last step that we have to draw to cross our T's and dot all of our I's? Got initiation, propagation, or termination. And again, by convention, we show the two radicals, and if you'll notice, the two radicals that wound up canceling out our propagation steps. If you show them running into each other, you'll also get your final product as well, so that's typically what we do. Some textbooks will actually just show it as an undoing of the initiation step. They'll actually just show the two radicals that you make in the initiation step going backwards to remake your initiator. Depends on the textbook we're using for this class. I like it, it makes more sense to me to take this radical and this radical and have them react to give us our final product. But again, that's somewhat semantics. Like I said before, you can pick any of them that you want.
So we
It's
get more
technically right.
down on the test if you put two cyclopentane radicals together to make a weird diet.
I don't know. If you did it right, which, and that's not gonna look like, that's not gonna be an easy one to draw.
No.
It'd be a weird one to draw. But if you were able to draw it correctly,
Okay.
then
I'm not gonna do
no.
that.
I mean, that's like saying, well, if I wrote with my left hand and it was super messy, would I get marked down? Well, no, if it's still right, I'm still
We
gonna,
like to read it.
right. Fine. No, just like by convention, we do the one that gives us this product, so. Bromine radical. Plus our cyclopentyl radical. I guess from the point of view of trying to, Zeke, I'm thinking about how you kept trying to make the whole thing, all of these steps add up to give you the balanced reaction. That's an argument in favor of making your termination the exact opposite of the initiation, because then they'll cancel out. And you'll just get the propagation steps adding to give you the net.
So it's just the propagation steps we need to
The
calculate.
propagation steps need to add to give you the balanced overall reaction. The initiation has to be pretty specific, depending on what the initiator molecule is. And the termination can be sort of open-ended, and we don't include those in our balanced reaction usually. But that would be one way to make the whole thing balanced,
Yeah,
would be to make your termination undoing the initiation. Now that I think about it. All right. So there's a lot of writing to these mechanisms, but the nice thing about this mechanism compared to like oxymercuration or the hydroboration or the boration reduction.
Yeah.
The nice thing about this one is that it comes in this neat package, always an initiation, always propagation, always termination. Oxymercuration and hydroboration, those are the two. Most complicated to say it too. For whatever reason, when I took OChem, this was the first mechanism we were shown. Which can you imagine learning this before you've learned SN2 and.
Yeah. it's kind of nuts.
I think it was because he wanted to get right into the synthesis because he was a synthesis professor. That's what he researched was organic synthesis, and so he said, well, this is important for synthesis, we'll do this first. But it was really confusing trying to learn that as your first mechanism. All right, and as we mentioned before, I just wanted to put the slide up here. So that we are showing this, there's our planar radical. Our first step on the propagation is that hydrogen abstraction, which gives us that planar radical, which means we're gonna get a racemic mixture with the R plus S. I think we have enough of a background now in talking about stereochemistry. We could write plus En, we could write racemic mixture like this, we could write R plus S, and not show any stereochemistry. I actually found, I think this might have been from Master Organic Chemistry. Skip forward here to a summary slide. Just to show. This is another way to do it. You don't show it as a wedge or a dash, you show it as a squiggly line and you write R/S to show that you get both of them. This isn't nearly as common, but I just want you to have seen it now. I think all of us would be able to look at that in context now that we've been talking about this, you would know what that meant. But just so you're not surprised by it if you ever run across that in the wild. All right, and so one of the ways that we can observe this is if we start, just like with our practice problem at the beginning. If we start with a chiral center and we put it through a free radical mechanism, we get a chiral center that's a mixture of both enantiomers, the R and the S. Okay, so it's just like SN1 like that, right? SN1 did the same thing. When you go through a planar intermediate, you lose that stereochemistry. All right, questions on the stuff up till now? From last class, and we just did last Tuesday's class in 20 minutes, so. This is just more practice with these, but we're gonna skip this and go talk about allylic bromination. We can come back to that at break if we want some more practice with the basic mechanisms. Right, so now what happens if we're looking at alkenes being present? We know that resonance affects these free radicals even more than an effective carbocation balance. To the point where we have it way easier. It's not approximately the same as a secondary radical versus a allylic radical. There's a difference in 40 kilojoules per mole there, which in terms of equilibrium constants and rates, at room temperature, that's going to be a rate of 5 kilojoules is a factor of 10. So 10 to the 8 faster at room temperature to pull this hydrogen off compared to that hydrogen. Roughly. That was the rule of thumb we used in grad school. It was 1.5 kcals per mole was a factor of 10. And kcal is about 4 times smaller than a kilojoule. So yeah, it's very significantly different in terms of their rate. Compare that to SN1 where we said, well, allylic and secondary are roughly just as stable. However, what happens if we put bromine with light and expose it to cyclohexene here? If we didn't have the light, what would we expect to happen? Again, it's not free radical. What happens if you just have an alkene react with bromine? We just do an addition reaction, right? We add bromine to each side, which do I use the term on the next one? So this is the reaction that we're repeating with then, right? So this is an example of the term that gets used when you have two things in the same vicinity, meaning on adjacent carbons, they call that vicinal dibromination. I don't know if it comes from the same root etymologically as vicinity, but I use that as a way to remember. Vicinal just means next door. So we don't want vicinal dibromination. If we are trying to do this in a controlled way to add just one bromine in a certain spot, we need this to happen, and we need this reaction to go in a way that we're gonna minimize this. Well, this is a second order reaction. It's first order in cyclohexene, first order in bromine. So if we want that reaction to go slowly, what could we do? How do you control the rate of second order reactions? Well, temperature is always a good, but that's gonna slow everything down, right? So concentrations, because temperature is gonna affect K. But the other way we can slow this down is by affecting that concentration. And so we actually, when we do this reaction, when we want to emphasize this reaction over the competing reaction, we can do that by keeping the bromine concentration as low as possible. Which you would think is also going to slow this reaction down, but because it's a free radical mechanism, it winds up being you don't need a lot of bromine at any given point for this reaction to happen. And so we basically can allow that reaction to dominate by slowing down the competing reaction. Right, and the way we do that is by using a molecule called N-bromosuccinimide, or NBS. Basically, NBS, the way it's packaged, basically always has a tiny bit of hydrobromic acid as an impurity in with the NBS. But if you add NBS and HBr as a catalyst, you actually get this. It's more of an equilibrium reaction. This figure is from Master Organic Chemistry. So I liked it better than the one in the textbook. But basically what happens is you generate a small amount of Br2. And this is again another case where the reason I went to this one instead of our textbooks figure is our textbook, there's some disagreement among textbooks still as to whether this goes through a homolytic cleavage to give you bromine radical directly, or if it makes bromine Br2, which then goes through homolytic cleavage. There's more evidence that this is, and it makes more sense when we get to some of the other details, that this step occurs. The net result is we're going to make bromine radical in very small controlled concentrations. Either way. But basically this is going to show us that we can make bromine in small concentrations kind of slowly, which is going to limit our competing reaction, but still give us enough bromine radical that we can expect the radical reaction to happen, especially if we're shining light on this constantly at the same time. Because if we're shining light on this constantly, if you shine light on just pure liquid bromine, it'll happen as well. You'll still make bromine radicals, but you can't turn all of your liquid bromine into radicals simultaneously while the reaction's happening. Basically, this process allows us to, as soon as we make the bromine, it turns into bromine radicals. As long as we're shining light on it constantly, because we're at such a small concentration. Plus, if you read up on any of the practical aspects of using NBS versus Br2, Br2 is really, really nasty to work with. I think I've told you the story before, me burning my lungs out with bromine when I was cleaning glassware. When at 18. And apparently I'm far from the only person who's done that. It's really, really nasty stuff. It's actually exceptionally dense. It's got a density, it's a liquid that's got a density that's almost 4 times as much as water. So it's really hard to work with. And it really it has a very high vapor pressure. So what happens if you try to use like Pasteur pipette, you have to use it in a fume hood, and if you try to use a Pasteur pipette, basically it won't stay in the tube part of the Pasteur pipette because it's so dense and has such a high vapor pressure that as soon as you pull it up, it starts dripping out. So it's really not very pleasant to work with. So even if you're not doing this particular reaction, N-bromosuccinimide among synthetic organic chemists is very much preferred because it's a nice white crystalline substance you can weigh out easily, won't burn your lungs, et cetera, et cetera. All right, so the net result, what we get here is if we're using NBS in the presence of light, that causes us to not go through the halogenation, the vicinal dihalogenation. And that allows us to preferentially pull hydrogen off in the allylic position where we have that resonance stabilization. And so what would our product then look like here? Bromine on the tertiary carbon, and we leave the pi bond where it is. And it's not, oh, and actually, that's not a stereo center anyway, right?
Yeah.
Two methyl speed, but even if it did have a chiral carbon, we didn't make a chiral carbon, it's not gonna have a preference.
Going back to the concentration thing. we have
Yeah.
Very low concentration of bromine and we're shining light on this solution, right? Would that affect the reactive molecule that we're starting with?
So basically, we're never gonna have a significant concentration of Br2. As soon as we form the Br2, it immediately gets hit by a photon and splits up into bromine radicals. So because we never allow this concentration to build up, that allows the free radical mechanism to continue, because basically we're just taking this and immediately shuttling it over to the free radical side. We never let it build up to the point where this gets to be measurable concentration. And so again, that's one of the reasons why the other textbook that we were looking at just showed NBS goes to, let me go back to the other slide. The way so we can compare this, the other way of drawing this. Initiation step. I think actually this might be, I think there might be another bond there. Another pi bond to make everything conjugated, but I'm not sure, so I'm not gonna add it in. It doesn't really matter for the sake of this next step. The other textbook showed it just doing that. And going straight to a succinimide radical plus a bromine radical. Because that really is the net result of, if you take this reaction and then immediately hit this with light, the net result is this kind of, except that we never really see this. This is basically an oversimplification, and then they hand wave it away and say, we don't care about that. This is more what's actually happening. And that's why it keeps this rate down. This is what I did a deep dive in last night and this morning, because I was trying to well, why would they draw it like that? Well, this is why, and this is why the rates and concentrations work the way they do. It's because this concentration never gets measurable.
We're
Get
really
more careful.
controlling is the concentration of the HBr.
Well, that's only present in catalytic amounts.
Right.
Just tiny amounts. So like a couple drops of that's all you're gonna need.
Because if
Anyway,
if there was a ton of HBr, then that would defeat the whole point, right?
then that would defeat the whole point, yeah. But if you're trying to do this react, you're trying to use N-bromosuccinimide to replace Br2 in that vicinal dibromination. Basically, you have to be really careful not to have any light shining on it. If you do it in the dark, literally keep light away from it, then you will actually build up measurable amounts of bromine. And then you can actually get it to go through the addition process. But if you shine light on it, that never happens. See, isn't this part of OChem more fun than Gen Chem, where we actually get to say, well, here's all of the variables, right? Let's talk about all of them exhaustively. At least it's fun for me.
Seems like more of a game.
Well,
It's a puzzle.
it never sits well with me with Gen Chem when people ask good questions, and I have to say, that's a good question, come back in a year.
Yeah. Now we're answering those questions.
Now we're answering those questions. All right, so let's do combination. Recap here. Give you a couple minutes head start, and we'll start working through these. And I'm just gonna take the right-hand column out on this slide here in a second, just give us space to draw. All right, for A. Racemic mixture?
Just the.
It's, yeah, it's because those two methods are identical. Yeah, that's okay, I'm just gonna keep calling you on it, because that was the one thing that kept David from a perfect score on the final, right?
Yeah.
So, like I've said before, I've never given a perfect score on the test, I'd like that to change, so I'm gonna keep calling you on it. Any other minor products that we have to worry about with the bromine one? No, because it's bromine, right? Chlorine, on the other hand,
Yes.
we're gonna get. Well, at least two, but probably you're gonna get measurable amounts of all three. The 1-chloro, the 2-chloro, and the 3-chloro.
That's 6 cents.
Yeah, so we're just counting hydrogens, there's 6 hydrogens that give us the primary, but they're less favorable. So that's gonna be a significant amount, I'm not gonna actually try to put a number on it, because it's. But it's gonna be double digits. Gonna be in that, because then there's 4 hydrogens that give us the 2-chloro. And only 2 hydrogens. That give us the 3-chloro, so. There's more hydrogens that give us the 1-chloro, but that's less stable intermediate. So out of those 3 options, let's draw out 3 of them real quick, I guess. Which one's the major product? Oh, yes, it did. Leave carbon off there, thank you.
It would be the secondary.
Yeah, the second one, because there's 4 hydrogens to 6 hydrogens, but it's that much more stable than intermediate. So push comes to shove, we're probably, I think when we looked at that one with propane, it was something like a 60-40 ratio. So it's still gonna be something that favors the secondary, but with the primary having a significant amount. But we can, so that does allow us to rank these from most to least, right? 1 and 2 are a little bit fuzzy. Probably this is gonna be our major product.
Definitely this first one over the second. Third one.
Definitely the first one over the third one, because there's 6 hydrogens to only 2. Right, so, and on the test, on the midterm, I'll make sure that I remember to write, like, if there is double-digit yield, I'll try to be specific. Just so, but basically what I'm gonna be saying is, if it's a chlorination. Show all of them and then just sort of rank them, 1, 2, 3. Yeah.
So it's like for the cutoff there, like people's stability primary versus secondary radical versus amount of hydrogens, we like. So yeah, 6 versus 4, those are more stable, so like definitely that, but then 2, so like where would you cut it off if you just?
So, go back to the slides from Tuesday.
Okay.
I believe that when we were talking about propane. And it was a 6:2 ratio in propane, secondary versus primary, and I think we said it favored the primary 60-40.
Okay.
So not by a lot, so but basically, and you're always gonna be dealing with even numbers. I guess not once tertiaries get involved, but.
Yeah.
That, so basically 2 versus 4.
Okay.
And I think I actually do a problem on the midterm where I say specifically just looking at number of hydrogens. I said leave out carbocation stability. So just give me the probability side of a molecule where all you do is total up the number of hydrogens, which ones are in which position to give you which. So I basically say removing the competing variable, which product has the most hydrogens in what ratio. So that's an oversimplification, but in case of a test where you can't go out and use outside resources, it's an oversimplification that kind of makes sense so that I can ask you probability-based questions. Makes sense, right? Okay. All right. This bottom one, this is one we just added, right? So NBS in light, this is a nice thing. NBS, like when we start adding in alkyne reactions and alkene reactions and free radical reactions, they're all going to be on the same midterm, right? So when we're talking about what are the keys to recognize, is a free radical versus alkene versus alkyne. It's NBS could be confusing because it could get lumped into some of the other three letter abbreviations we use, but it's still got lot. It's still got light there, right? So the light is all of these for your free radicals is a really good flag. Okay, I know this is going to go radical. And then it doesn't, oh, now I remember what that, if I put myself in the context of it's a radical reaction, now I remember what NBS does. And maybe that's overly optimistic in some cases because it's still a testing environment and stress and all that. But at the same time, that's kind of how my mind works, is to chunk stuff up. I can ignore alkenes and alkynes as soon as I know it's free radical. And then use that, okay, what was that last free radical reaction? What did it do?
Exactly this happened, you go. It's like, oh, I see the light, but I don't remember the NBS, but it has to be.
But it has to be bromine. Yeah, exactly. Right, so the product just. And again, not a racemic mixture, not a stereocenter. If it didn't have that second methyl group, now it's a stereocenter. And we would expect racemic mixture of R plus S. All right, let's do these other three. Sorry. We get here. Bromine was super selective on the same molecule, but iodine's too slow, too stable. Does it matter that that's a benzene ring? But that actually, we have to go back a slide to add a caveat to the one we just did.
It'd be the allylic hydrogen that's the.
That's the only one. So it's not allylic if it's a benzene ring, they call it benzoic position instead of allylic, but it's the same basic result, right? Because it's got all that resonance stabilization. And what did we get here? Not allylic. Right, so we're looking for what's that most substituted. hydrogen. So we're gonna put it in that tertiary carbon. He's gonna get it from me. Yeah, that, good catch.
I'm just, it's still in my own head as well.
Yeah.
'Cause I'm not too good.
Repetition is our friend, right? All right, the one point that I want to go back and cover with the allylic one that I forgot to make this point a second ago. What is our intermediate gonna look like? For this one, for our carbo radical intermediate.
Radical, tertiary, or
Radical on the tertiary carbon.
resonance, possibly.
And this is what I wanted to make the point. Is that this is stabilized because of resonance, right? Which means that there's actually. So that would look like drawing the resonance structure arrows would look like this. We're actually gonna get measurable amounts of both of these bromination products. We're still gonna favor this one because this is a larger resonance contributor, right? Because it puts it's tertiary with resonance stabilization. This is primary with resonance stabilization. We're still gonna make some of the product that comes from this, but our major product would be this one. If we started from this molecule though, it's a little bit like a rearrangement where we have to pay attention to. Is it gonna change? Like, that's the allylic position initially, but once we start doing this resonance stabilization, this is actually gonna become a major product. And because when we have a resonance stabilization, we have to look at which of those is the major contributor, which of these resonance structures is more stable to determine which pathway is it gonna go through most of the time. Since either of those two positions could be brominated.
If we started from this molecule, not the radical version, but just the molecule, would that hydrogen on any of those hydrogens on the left side or the top side be stolen, so that ignores it's included?
Right, so in that case, if we pull the hydrogen off, now all three of the hydrogens we might pull, or all three of the carbons we might pull from, they're all allylic, but they're all primary. So in that case, either of those would actually give you the same product at the end, right? So then we actually, now it's a numbers game again. There's three hydrogens, we would actually expect, put them on these carbons in a 2-to-1 ratio. Compared to that one, because 3 to 6 in terms of number of hydrogens. Good question. It's a little bit of a house of cards, right? It's simple enough as long as they give you simple molecules. But there's, it's a pretty deep rabbit hole you can go down when it comes to some of these, which is why if I gave you this on the test and you forgot to consider those and you just put it over here, you forgot to consider the resonance, that's still at least a 2 out of 4. 3 out of 4 if you remember they can resonate, but you forgot about these ones. 4 out of 4 will be remembering all of those aspects of it, right?
Isn't there could be cases where like the first resonance structure that we draw is not the more stable one? So like if there wasn't that methyl group on the 3 carbon, but instead there were like 2 methyl groups on the other side of the double bond,
Yeah,
right?
we're still a little bit before where we take our break a lot of times, so let's do one that is a little bit simpler. So in this case, we're going to do a hydrogen abstraction from one of these 2 methyl groups, right? So our intermediate is going to look like this, and I made on purpose, I made them like symmetrical, so we don't need to worry about the other wrinkle. So this is one of our resonance structures, but our other resonance structure is going to look like this. Right? This is the more stable resonance structure, to your point.
Yes, exactly.
And so we would actually expect to see the 2-bromo. I said be 3-bromo 1-butene product more commonly than the 1-bromo 2-butene. Because this is the more significant resonance contributor, the more stable of the resonance structures. So when you have the resonance, when you have resonance stabilization, just like with carbocations back last quarter, we still need to be paying attention to, okay, well, out of these, what's my best option?
That would be tremendous.
And that one would give us an R+S. This one would. All right. So all we did, we only added one more mechanism in the first half, right? Of course, we keep doing that every single lecture for the rest of this, course. That's still a lot of mechanisms by the end. And it'll be close to that. There will be a lot of mechanisms, but if we add them slow enough, we make them all make sense along the way. Then with a little bit of review before a test or a standardized test, it's easy enough to come back and remember that, as long as we make them make sense now. It's like the MCAT has an OChem section, right? It's not a fun part of the test for most pre-meds because you're usually doing that in the year after you finished your OChem, when you have to go back and review your OChem. And there are some mechanism questions, and it's all multiple choice. So it's not like there's partial credit. It's not, again, that's probably another reason why OChem has a bad rap among pre-meds, is because their most recent recollection of it is having to review it on their own for the MCAT, not the actual class. Because that is a lot, but that's why we're taking our time, making them all make sense now, so that when you have to go back and review it, you'll be in good shape. Plus, hopefully you'll feel comfortable enough if you're still here or around when you're taking the MCAT, you can always come back. I have had students email me MCAT questions when they're prepping for the MCAT after they've transferred too. So I will always be your OChem instructor, even if you're at another school.
Thank you.
All right. Absolutely. Let's take a 10-minute break. Let's come back at 5 after, and we'll add one more mechanism today.
That was fun.
I'm glad you enjoyed it.
I did enjoy it a lot. I only remember probably like 5% of it. You know, I know what you're drawing and I know the orbitals, I know those pieces, but like OChem I liked OChem better than Gen Chem, much better than Gen Chem, but I still struggled. It was still hard. And then biochem is where I finally like did better.
Yeah.
Yeah.
Yeah, I mean, there's so much more, seeing all the mechanisms fit together, you know, so.
Yes.
It makes a lot more sense for somebody who did well in cell biology or micro.
Yeah, and there's kind of like, not that there's not a purpose to this, but like, there's a purpose like where it's going. Like, I know if I'm in glycolysis, I know what I'm starting with, I'm going to finishing with, I know why it's happening. I know where it fits into the larger mechanism of aerobic cell respiration and anaerobic cell respiration. Like, I know those pieces, and so it's easier than I'm like, this is like more abstract. I'm like, well, I guess if I'm trying to make the thing, and I need the thing, then I need to know how to make the thing.
Right.
You know, yeah.
So it's synthetic
Yeah.
OChem definitely, and also probably the number one place that most biology or biochem people see this again for radicals especially is talking about cellular respiration
Right, yeah.
and production of oxygen.
Yes,
And how it
exactly.
makes peroxides, and that's what free radicals are.
Exactly.
Be setting them up to actually understand that, even if they can't come, I don't expect them a year from now to be able to draw this mechanism.
No, yeah, no, totally. And it's funny, you reminded me whenever I would talk about anaerobic cell respiration, I spent, because this is not majors, right? So I'm like talking about redox reactions and kind of like trying to help them understand it. And I would use the analogy of filling your car with gas.
Mhm.
And like how each time you moved an electron, it looks like your piston moving in your car, and release a little bit of energy. Or you could just fill your car with gas and light it on fire, and your car will explode. I'm like, there's an energy that's being
Yeah.
released, but we wanna slow that movement of electrons to oxygen as much as
Right.
we can. So then it gets in a little bit easier to talk about NADH and FADH2 for them to go, oh, that's the purpose of those things. Especially remember, like I said, for the non-majors, because like they're like,
Yeah,
you know, that section's hard. It's funny, it's not as hard, it's always surprising to me, it's not as hard as transcription and translation. Because transcription and translation is plug and chug. It really is. It's like if you know the codon, I don't know anybody,
Yeah.
but if you know the codon, then you know the amino acid.
right,
It's just easy, and then you just gotta know like the parts that you get the ribosome and everything else, but it's kind of simple. But they would always like their husband explode. I used to
Yeah.
teach non-majors bio, so it was like, you get into like transcription, translation, and it's just like the blank looks in the
Yeah.
class. I'm like, okay, let's take 5, like,
Yeah.
let's just. And then we go to new games and stuff like that.
Yeah.
I can understand it. but-
Carl went all out when we went over gene coding, because he's a gene guy, so.
It's cool, it is so freaking cool, I mean, of course, given I was doing nominated, so we never talked about like genes or anything like that, it was really simplistic, it's like, if you're crossing over, you're crossing over, like, there was nothing that, we didn't talk about like things that travel together, or anything like that. And, but it was super fun in genetics to look at that stuff
Yeah.
and how that works, and when I was in school, we got to play with fruit flies, and so it was like, it was really fun.
that's, yeah, I guess we don't offer genetics here, do we? Majors.
No, because it's usually an 100% class.
Is it?
Yeah,
I
when it was
was
under
second year when I was in college.
Oh, dang, no, it was under it was a core
Oh,
class.
okay.
It was that and micro ecology, cell and molecular biology, and evolution was what it was.
I wasn't a bio major, biochem major, but all my roommates were not the same area for a biology major.
Fair.
And so I was paying attention to everybody's schedules to some extent, and but I guess it was the second semester, second year, so that is starting to get into where it could be considered upper division.
Yeah, that's just, I mean, on the sex
Yeah.
day, that's how it was the sex day.
Yeah.
The upgraded courses, but no, it was fun, but he didn't let us use fly nap, so we always had to put the flies in the freezer. To get them to like slow down, and then when they start getting warm, they start moving around, so you put them back in the freezer, so it was hard to count the flies. But they kept waking up. What is your weight status again? So, yeah,
Fun.
yeah, it was super fun. So.
Well, you're welcome to stay for the second half. if you want,
I
but
wish
know
I
you're
could,
just-
I can't,
Yeah.
I gotta get this thing done for meeting we have tomorrow, so, yeah, the meeting's not stopping.
Well, have fun with that.
Thank you, I know, right, I know, it's like whenever you come and do a class evaluation or like especially in science.
I know. This is what you gave up when you became that.
I know.
Yeah.
If I hadn't had meetings, I was going to go and ask if I could set up for a class, because they're gonna do taxonomy of vertebrates, I'm like,
Let's do that.
Pioneer, we were supposed to get like 8.5 inches of rain over the course of a week.
Yeah, I think Monday, Tuesday, maybe Tuesday, Wednesday, it's supposed to be snow here, but right now I think the projections are all, like, we're supposed to get like 4 inches of rain
Yeah,
Saturday, Sunday, Monday, and then 8 inches, maybe 10 inches of snow.
it's gonna be.
But it's, you know, half a degree different either way, could really change that. That's the thing with meteorology up here in the mountains.
I really hope it doesn't rain much, because it's gonna freeze over overnight, and it's gonna start snowing, and it's just gonna be like, the roads are gonna be horrible.
Roads are gonna be horrible, it's gonna be impossible to clear.
Yeah.
You know, stock up on your Shirkin for your snow blower before this weekend, because it's gonna be. Yeah, when it gets to the really, really saturated, the snow that splashes when you shovel it. It's like, I don't even bother with the snow blower though, because it's like, it just dumps it up and sits in there.
It takes longer with the snow.
Yeah.
than it does by hand.
Right. But my back will be paying for it for days.
Yeah. I found this, my mom actually found this back brace on Amazon, but it's like an elastic one, it has like 4 things, so you go one Velcro this, then Velcro that, then Velcro this, and it's like, you can get it just tight enough, and it's like light, it doesn't dig in anywhere, it's like the one gets water. That thing's incredible.
Yeah,
It's like 15 bucks.
I mean, at the very least, it'll help remind you to keep your back straight.
Oh, yeah, no, it makes a huge difference. Like
Yeah.
anytime I'm doing any sort of thing where I'm just having to do repetitive lifting of like medium things or lift heavy things, I wear that. And it's like, it makes a huge difference. My back is not hurt afterwards.
I'll have to look into that.
Yeah. It was on Amazon, just look.
Okay.
It's like 15 bucks.
Okay, yeah, that's the, when we bought our house, it was a big gut job. And I put in all the flooring myself. And we had a newborn at the time. And so it was like, wake up, go work, come back, eat dinner, work for 3 hours, sleep for a couple hours, then the baby wakes up and needs to be fed. And but one of the very, like, that was one of my first consolation, or like, okay, I'm getting older, I need knee pads. For flooring, like, you gotta have knee pads, especially once you hit 30, but just do yourself a favor, even if you're in your 20s, and
Me past 18 years old.
yeah, if you're doing it on a, like, I think when I was 22, one of my summer jobs before I started grad school, I worked at a Petco during the day. And then in the mornings before Petco opened, I worked as a gardener with a guy who was like, he worked on $1 million houses. We did like these really high-end houses, gardens in San Diego. But he was like 70 years old, and he still smoked like a chimney, and was up at 5 a.m. doing gardening stuff. But he instilled in me, it's like, always knee pads,
Yeah.
just always.
It's like, inadvertently, that's not to smoke as well.
God, I gotta say, there were a few mornings that as a 22-year-old, I showed up to garden hungover at 5 a.m, and he would light up a cigarette, and I would just about throw up right on his shoes. So yes, that really put a kibosh on, ever smoking. All right. Let's do. This is just more of the same ones we were just going. Oh, I did split them up differently. Okay. All right, let's look at B. In particular, in this case. So a little like bromination, now we have 3 bromination spots. Are there any that are going to be more favored?
Probably the second.
The secondaries, yeah. There's
There's
gonna
two
be,
of them anyways.
there's 2 of them. And that gives us our intermediate is more stable because it's a secondary with resonance instead of a primary with resonance. We'll still see some of the primary product, but our major products. Are gonna be this. R plus S. And. R plus S.
Probably would be a good idea to just always draw the intermediate out with the resonance.
With the resonance in particular, it's a good idea to draw. What you're looking at, so we could put it here. Here or here. They're all going to be resonance stabilized. And that means there actually is a significant, so one of those the resonance structure for this one. Give us that product. But that's the same as the second one I drew over there.
Yep.
So, yeah, definitely not only draw your intermediates, but draw the resonance structures of your intermediates, which can be a lot of potential intermediates in drawing to settle this. But it's a way to make sure you get the right major product, is draw yourself all the possibilities and then just say, okay, if I'm just looking for the major product, you can start, okay, well, I know it's not gonna be the primary. Because everything else is secondary.
That radical vessel be involved in this?
So we will make some amount of. The product that comes from here. But even this, even if we make this, its resonance structure. Would look like this.
Right.
Which, again, that is a third product now, but out of these two, this one's favored.
Right.
So we're, again,
We're
with
pulling
the,
strings.
we're pulling at strings, and that's good because it makes the point that these radical mechanisms, you get a mess of stuff. In this case specifically because of the resonance, but even with the other ones, especially with chlorination, you're gonna get a little bit of everything, double digits of everything, it's possible. And it's not, so, and that's not always a recipe for getting a good yield. Like that, you know, most synthetic chemists aren't gonna use chlorination unless there's no other option. Because it's just, in general, even a bromination followed by an illumination, followed by an anti-Markovnikov bromination, 3 reactions in a row might still give you a better yield than your 40% yield that you would get on a primary carbon. So it's worth the sweat and tears in a lot of cases, yeah. Especially when you get into big industry numbers. And I know I've mentioned my buddy who works for Chevron before. But if you crunch the numbers, like shaving off or getting an extra, 0.2% efficiency in a oil refinery could be billions of dollars a year. And that's going from 94% efficiency, 94.2% efficiency can be huge and make your career. Get your name in engineering textbooks if you invent a piece of equipment to do it. And same is true in pharmaceuticals, especially, think about something like aspirin, something that they make billions of tons of it every year worldwide. Coming up with a mechanism that's just a little bit more efficient winds up being a big deal. I think there's not a whole lot of low-hanging fruit left anymore because most of those optimizations have been done. But there's always room, there's a reason that we're still studying synthetic organic chemistry because there's still new mechanisms being discovered and understood and things like that. So.
Say there's molecules in.
Well, and there's new molecule, they're making new medications, they've discovered.
There you go.
There's still. So, and then actually, this is one of the few places where I think that AI actually shows a lot of promise is in screening potential molecules for medications. If you feed into an AI model that looks at, okay, well, here's the active site on this protein that we want binding affinity of in this range, but we want to make sure it doesn't interact with this binding site on a related mechanism that's maybe something that causes it to be addictive, for instance. So we want it to block pain, but we don't want it to be addictive. You can put numbers to all that and then just throw it into a database that says, okay, well, if we put this functional group here, this functional group here, that functional group there, now all of a sudden we've got a molecule that doesn't occur in nature that nobody necessarily would have thought of on their own. Will it work as a medication? I don't know. We need the synthetic chemist to make it, and then the biochemist can try it on mice. And or then the biochemist would take that molecule and test it on those enzymes to see if the binding affinities were what they expected. And if they are, then they take it and they give it to the biologists who test it on mice. And if it's promising in mice, then it moves on to larger, further up the evolutionary chain until you get to human testing. And this is why it's so wildly expensive to develop new pharmaceuticals these days. It's not the old days of, I made a new molecule, I'm gonna eat it and see what happens.
Good old
The
days.
good old days.
Have you heard about septic?
Yeah,
Yeah, I looked that up on, Moleview, and it just gave me like a scary figure.
so where we're getting now is it's not a small molecule
Right,
drug anymore. Most new pharmaceuticals these days are small polypeptides, meaning there's several amino acids linked together that mimic a protein interaction. And then sometimes what they'll do is they'll take that and then they'll swap out a sulfur for a chlorine or something like that.
okay,
Um,
well, it's scary.
yeah, and so, yeah. So hit the 2D to 3D. There it is. So that is a polypeptide with a fatty acid chain attached to it as well. That's not something that you could come up with free, right?
Yeah, you know, that.
Probably not AI at this point because it's been approved for use in humans, so that means it was probably 10 years back that they actually first discovered
It takes
it.
a long time.
It's a
It's
really
a
long
long
time.
time.
Because they've got to study longitudinal effects. They don't want to approve something and then find out that it causes severe issues 3 years down the road. So there's a certain time frame, but basically it's at least a year after human trials before they can actually approve it, unless there's some very specific case for rushing it.
What about the ones that are like, mimicking methamphetamine? The
So
reason I looked this.
What, just different like amphetamine analogs?
Well, they just mimic it really towards the.
Yes.
Methyl group or something and binding affinity.
So those are mostly small molecule. And so basically you start with something that you know that's called what's the term for it? Not inspired drug discovery, but there's some term specifically for taking a molecule that you know works, but has targeted drug design. Targeted drug design basically says something like, okay, cocaine is a perfect example. Cocaine was used as a topical anesthetic painkiller for in the Old West days up until World War I, basically, but had its side effect of being horribly addictive, and likely to be abused. And so they took cocaine structure and they said, okay, well, what if we chopped off this chunk of it and replaced it with just a methyl group? And then they tested it. Does it still have the topical anesthetic properties? Yes, no. Depends on what chunk they chopped off, right? Is it still addictive? Yes, no. But basically that's where any painkiller that has cane in the name,
Like Novocaine.
Novocaine, lidocaine, those are all cocaine derivatives, cocaine analogs, where they just chopped off the part that gets you high and makes it addictive. And so, but they're doing the opposite right now with, I think the current term they're using is research chemicals, but it's basically what they also call them designer drugs. Where they're going the opposite route. Here's a molecule that's illegal, but if we chop off a nitrogen and put a chlorine in its place, now it's a different molecule and it's not illegal anymore. But it has all the same similar effects. So they are still doing that. That's not happening as much. A lot of those have already been eliminated for use in terms of medical use. Okay, it still gets you high. It's not what we're looking for. But that's exactly what people working in underground labs across the world are actually looking for, and then they sell it online.
I just get concerned when someone asks me like, what is this molecule type of thing? I look it up and it's pretty much methamphetamine.
Yeah. That's exactly why.
Like, oh, it's pretty much meth, but it's not.
Right.
Exactly.
And there's a lot of other stuff that's similar that you can find, their Ritalin is technically a different molecule, but it's still basically a substituted amphetamine.
And benzodiazepines, you can kind of just.
Benzos are the
you
same
can go
way.
in deep hole changing stuff and it's just gonna have.
And it
the same
gets
effect.
very subtle effects like Valium versus Xanax versus Klonopin
It's like
versus.
Elimination, half-life and.
Right. Exactly, and just how intense they are. That's exactly how fentanyl was discovered too. And things along those lines.
Sorry, steer off track.
No, it's okay.
Jeez.
It's good. It's a good discussion, but that's one of the reasons why So a lot of it's pretty easy to mess with brain chemistry. So a lot of the psychoactive drugs have been discovered and either are being made underground and passed off as meth when they're not really, or passed off as molly when they're not really. But they're easier to make because they're not regulated. But a lot of the stuff that's going on with weight loss drugs and diabetes-based drugs or diabetes treating drugs and things like that, those are larger molecules, usually a couple amino acids and some other random stuff in there. And those are the ones that would be really hard to design from scratch as a human, but something that a computer will just scan through. Oh, here's a list of 150 different possible functional groups. They all have this size and this electronegativity and this dipole moment. What could I put on a benzene ring that's going to cause it to fit into that active site over there? And so it just screens through thousands of them. There was a group that our research, we shared an office with another computational chem group that worked on proteins. They were not doing quantum-based calculations. They were using called molecular dynamic simulations. But they did a lot of stuff like that where you would screen out a ton of different potential molecules, and specifically because my active site is this big and has these hydrophobic, hydrophilic regions, what could fit there?
That's also why like the quantitative solution of protein folding from just knowing the initial structure is such a big thing. Because it can be really hard to get a protein purified, crystallize it, do X-ray crystallography on it to actually solve the structure. You can just plug it into AI and be like, here's the genetic code, what's the 3D structure going to look like? Then you can figure out what the active sites are going to be and like design drugs for that.
Yeah, you don't actually need to get a crystal, because getting a crystalline sample of a protein so that you can run X-ray crystallography on it, getting back in the days before the computers could actually simulate this stuff in the the dark ages of the mid 2000s, there would be somebody's entire PhD project. It would take them 3 years, 3 to 5 years to crystallize one protein, take X-ray crystallography of it, and then work out the structure. That was like a 3-year project.
I spent a year and a half trying to get a human TUT2 to crystallize.
Right.
I could not get enough of it, like to get a crystal going.
Exactly. And the people that work in the, like you're saying, the people that work in those labs will tell you that getting the crystal is actually harder. Once you get the crystal, the X-ray crystallography is just a whole bunch of trig in 3 dimensions.
The computer does it all.
And the computer can do that even in the mid 2000s, the computer could take the data and do that. So it was actually the lab, the research part was actually in getting the crystal structure. And molecular simulations, molecular dynamic simulations have come a long ways towards at least getting close to what the 3D structure should look like. Any of you take Chem 118 or that intro to biochem class we have here? There's a lab we do in that one sometimes where they actually crowdsourced protein folding mechanics that by turning it into a game and assigning points to different interactions where you have to like, I'm going to drag this amino group over here, and I'm going to put this alcohol group. I'm going to drag this alcohol group over there, and you're trying to minimize unfavorable. Basically, you're trying to find the most stable structure, the lowest point on the potential energy surface. And then they took all this data from these people playing this game and competing for high scores. So you put a high score to it, and people will spend hours on it, right? They basically use human brain power to get close. To do things that the computers couldn't get past. The computers couldn't quite figure out certain things because they lacked the human intuition aspect. And so they actually did publish some good stuff. But if you're interested in playing that game, it's called Fold It. It's still active, still has active servers.
It's called
Fold It, one word. And it actually is kind of a fun game. Yeah. And you're contributing to the sum of human knowledge by playing too. So when you get told, you're just playing video games, you're not doing anything useful, you can tell them, no, I am. All right, half an hour. That was a fun day. Let's talk about the mechanism for a reaction we already know, those anti-Markovnikov addition. So Markovnikov addition of HBr to an alkene group. It was just acid catalyzed, right? It made carbocation intermediate, and then the bromide acted as a nucleophile. If we did that with impure, and again, I gave you the historical context. If you had impure reagents, basically this came down to a certain chemical supplier had HBr that had some peroxides mixed in on accident, just like as a 1% impurity. So this was just one specific case. They were trying to replicate Markovnikov's research to better understand Markovnikov's role, and they kept getting anti-Markovnikov product. And it was because the bottle of HBr that they had ordered had some impurity and had sat on the shelf for too long. And eventually they ran the analysis on the reagent bottle, because that's not usually your first thought. Your first thought is, well, Markovnikov's full of shit. He's publishing data that's not real. I can't replicate it. It's not my fault. This is his fault. Eventually, though, they kept trying. They kept getting this product really consistently. And I don't know if they were in contact with Markovnikov or if they figured it out on their own, but basically they were able to come to the conclusion, well, let's order a fresh bottle of HBr. And see, and when they got a fresh bottle of HBr from a different supplier, they got the Markovnikov product. So then, okay, well, obviously our HBr is wrong. There's something wrong with it. And so eventually they figured out that there was peroxide present in the bottle. And then they were able to take peroxide and intentionally add it to the fresh bottle and got the same thing. So they were able to confirm. So we saw this already. HBr in the presence of a peroxide and give you the anti-Markovnikov addition. But now we actually have the background to talk about the mechanism for it. So it turns out what was happening, and it was just peroxides are unstable enough that they don't need light. If it's a peroxide, just the presence of heat is enough to split it up. Light will also do the same thing. So sometimes we'll see it with light. I typically, because we use light in this class as a key to tell us to think free radical, I typically will write light as well, but in certain cases like this, heat works well enough. And you make two alkoxy radicals. And what those will do is they will actually pull a hydrogen off of the HBr to make a bromine radical. So instead of using bromine to make a bromine radical, if you do this, you make, and so this is also in place of using NBS to make a bromine radical. This is another mechanism for making a bromine radical. But the result of this is that because we make the bromine radical in the right concentrations, we actually wind up with it going through an addition reaction. Where instead of doing a hydrogen abstraction, it'll actually make a break the pi bond. And then once we break the pi bond and we make a free radical with it, it's going to find another HBr molecule and continue the whole process. Termination step is usually written as, or in this case, it's written as two bromine radicals running into each other. But again, these two running into each other work pretty well too. And this is still where I'm still not satisfied with the explanation for why this goes through an addition instead of a hydrogen abstraction. So there's still an allylic hydrogen here, right? And it's still a bromine radical with an allylic hydrogen, which we just did a whole mechanism based on that. So I'm still looking for more sources that explain why. If you do it with peroxides, if peroxides and HBr is your source of bromine radical, you get the anti-Markovnikov addition. But if you use NBS as your source of bromine radical, you get the allylic bromination. It is, so there's more details there that I'm not satisfied with yet either. For now, for the sake of this class, in all likelihood, it's probably a competitive reaction. We're probably
It's like
seeing
this
both.
whole propagation step is. There's more to.
Yeah.
just these two steps.
And it could be something like the fact that we have an alcohol around, like as a protic solvent, it could be a solvent issue. We don't usually talk about solvents when it comes to free radical reactions as much, but it could be something about the solvent being protic that causes it to do this. For now,
So I was gonna ask like a similar question, why is it just another bromine radical?
right, because we're passing up the chance to have a resonance stabilized radical. And again, I'm not satisfied with how it's presented in any of the textbooks I've seen yet to explain why it does and doesn't do that. But here's a good summary slide. For now, is if you see NBS, put it in the allylic position. If you see HBr and peroxides, it's addition anti-Markovnikov. And if you see HBr without peroxides, it's addition Markov. And I will do more digging over the weekend to try and understand why the peroxide one goes that route. So here is the result of what I found last time I tried to answer this question. Low concentrations favor making the most stable radical intermediate, which is the allylic. Higher concentrations favor making the addition products. Right, so with that figure back up here, so we can think about that while we're so in low concentrations. Again, I'm still not satisfied with this, but you can kind of see if you can keep the concentrations low enough, that allows the bromine to be more selective. Basically, because on average, if it's lower concentrations, it's running into things less often. It's running into things less often, then there's more of a chance for it to run into something just so to get the more favored radical intermediate, the allylic one. But at higher concentrations, that's driving the reactions to happen faster, and you tend to see the addition because it's just going to bump into something and react faster. Thoughts?
It's gonna require some time.
Yeah, because so for like NBS, right, we're using light.
Right.
Like that. And so if we have a low concentration of bromine but we have an entire field of light coming in. As soon as that bromine pops off, chances are before it hits something, it's gonna get hit by a photon,
Right,
which will split it,
right,
and then it goes radical.
right.
Versus if we have a high concentration of bromine, there's gonna be enough of it before it gets hit by a photon, it'll react with the alkene.
Right, and I guess there is a fourth one we should put on here. Cause that gives us the dibromination, right, the bismol bromination. So in really high concentrations of bromine without light, we get this. In low concentrations of bromine with light, we get the allylic position, but both of these involve making bromine radical. This doesn't make a bromine radical, and neither does this. Both of these make a bromine radical. But in the low concentration of bromine radical, we get the allylic addition. In higher concentration of bromine radical, we get the addition, the anti-Markov addition. Right, and so in theory, if we ramped up the concentration of NBS enough and didn't shine light on it, or at least not much light on it, or if we did NBS in the presence of peroxide, we would probably get this. But it's the low concentration of bromine with the light allows us to make the allylic bromination. Higher concentration of bromine with light or peroxides is going to give us one of the addition products.
I'm curious if it would be a fun experiment to do to have a couple different variables, like do the NBS reaction, and then in one keep like several concentrations constant, and then change the amount of light for each one, and then some keep the light constant, but change the concentrations of the alkene, and see if that would affect it too.
Yeah. If we had a research grade GC
Yeah,
where we'd be able to actually separate these things out and get quantitative numbers for concentration, we could do that.
well, that'd be so.
I think we lack the ability to actually get meaningful concentrations or ratios of the competing products here. But yeah, you would. Based on our current I'm putting myself with this group too, based on our current understanding of these mechanisms, I think that you would see. You'd see different yields by changing the amount of light and keeping NBS constant. And I actually have a UV lamp that I use at home for curing 3D printed stuff. It will actually use to initiate some of these, and we can compare it to, if we have a good weather day, just taking it outside and putting it in the sun. Sunlight up here is pretty intense. And last time I think we actually got, it's a cheap UV light. For curing, and if I recall correctly, last time we actually got better results from the sunlight. Better yields from the sunlight than we did from the UV lamp. So there's a lot of variables that go into this, and it's again trying to actually get real world results to match the theory is the trick. And this is why they say in theory it goes this way. Actually making it work that way and getting the results to match that is trickier. Under the right conditions, they'll match. I'm not sure if we have the right conditions half the time here.
It is definitely one of those where it's like not intuitive to get that theory practice.
Right, exactly. So, but as far as what we're gonna do in the theory part and for this class on paper, this is our distinction. HBr versus HBr with peroxides versus NBS and BR2. And you see BR2, don't worry about the fact that this might have a small amount. Right, we're not looking at competing mechanisms at this level. We want to understand why it goes one way versus another, but don't get too hung up on it. I say as though we haven't spent half an hour talking about it already.
With the NBS, reaction pathway, would that still happen in the safe solution?
This one? Yes, because so HDR was part of the process of turning NBS into a bromine radical, right? Basically, you needed that N-bromosuccinimide needed a bromide to come in and attach to it to make Br2. And you just did a quick proton transfer and leaving group leaves for that to happen.
So basic solution.
Basic solution might not work. But like I said, I found numerous sources that basically said that NBS always has HBr in small amounts. So you might not even need to add HBr. Just using NBS, because of the way it's produced and synthesized and the way that it naturally breaks down, there will be small amounts of HBr in it already. If we wanted to speed the process up, and this would be another variable to look at for your study. Okay, how much HBr do we have? Because the HBr making Br2 might actually be more significant than changing the NBS concentrations, changing how fast the NBS breaks down. All right, here's one that we're not really gonna look at the mechanism too much, but this has fun everyday applications. A lot of organic compounds will naturally break down in the presence of peroxides. And the thing is, there's almost always small amount of peroxides around if you have oxygen around. Because oxygen itself is a very reactive molecule, right? And so this is actually one of the reasons why spices lose their flavor. You have ground spice where you have a lot of surface area. It's not just that the essential oil winds up evaporating off. There's that aspect of it too, but even if you keep it really tightly sealed, you can still wind up with it sort of losing its flavor over time. And that's just due to the presence of oxygen. And the other aspect of this is this also applies to pharmaceuticals. So the reason that medications have a shelf life is mostly due to oxygen. In the higher end pharmaceuticals, especially stuff that's expensive to make and buy, when it leaves the factory plant, it'll actually be packaged with an inert gas when it's sealed in an airtight container, right? So rather than just let the atmosphere fill it up that has 20% oxygen in it, which is going to break down your product, they'll actually just fill it with just straight nitrogen or with argon, something that's not going to go through this process. So the shelf life of a lot of pharmaceuticals, as long as they're sealed, their shelf life doesn't start to degrade or doesn't progress, I guess. The pharmaceuticals don't start to degrade until you open it. Just like a soda doesn't start going flat until you open it, right? Different mechanism, but same logic. And so a lot of times if you bought a Costco multi-pack of aspirin, and you have 6 aspirin bottles, if you're going through them one at a time, you don't open all 6 when you first get them. It probably could last you a long time. If you open all 6 when you get them, their shelf life is about a year.
That's good enough.
Right. You say that, but I have like 3 open bottles, so I don't, because there's one upstairs, there's one downstairs, and there's one in my bag.
There's one in your car. Great example of that is glucagon, because it's super expensive and it actually comes in sort of 2 vials. One of them has the powder in it, the other one just has like DI water, because you don't want to have it in an aqueous solution, because it'll degrade in that. And there's a bigger gas in the powder vial and salty.
Right.
It's like $400 or something for one dose.
Yeah, exactly. And that's, a lot of times, especially the most expensive pharmaceuticals, you won't see them, even if they're administered via IV or injection or something, they're not stored in their aqueous form, because water will also have some oxidants in it as well. Trying to think of the other one. And that's actually one of the main things that a lot of pharmacies do is actually making the suspensions for these short shelf life antibiotics. For toddlers, right? Toddlers can't take a pill, so they need them to be as liquid form, but they don't store it well as in liquid form. They'll make up the suspension when they get the prescription, so that the shelf life of the powdered form is a lot longer than the liquid form. Stuff that they go through all the time, you know, the penicillins or whatever, that kind of stuff, they'll just get a shipment of it and keep it in the fridge. And just, it's cheaper than having them spend their time to actually reformulate it every time. But some of the more less commonly prescribed stuff for kids, they wind up doing that approach. All right, so we'll look at this mechanism. This is not one that I'm likely to test you on, and it is a pretty straightforward mechanism. Your initiator in this case is just initiator, basically some other radical. If there's any radical present, you're going to wind up with it doing a hydrogen abstraction on whatever your alkane is. But there's lots of initiators just present in everyday life. This is one of the reasons why antioxidants is such a big health market, is because there's always oxidants. We don't really call them oxidants, oxidizers, present in small amounts. Even in your body, no matter how clean you live, or what time frame you're in, your body produces small amounts of peroxides in the process of breaking down oxygen and sugar. Right? There's an intermediate step in the electron transport chain where you wind up with an oxygen single down to another oxygen as an OH, and then this is attached to, I think it's a manganese, maybe it's iron, that's then attached to a protein. And it's kind of, the manganese is sort of like attached on all three sides to this protein. So O2 comes in, attaches to the manganese, and just sits there, and then what happens, the electron transport chain takes an electron and adds it, or a pair of electrons, and adds it to the O2 and turns it to a peroxide. So you basically are you're reducing the oxygen, which makes it more stable in the long term. But to get from O2 to CO2, you have to go through an intermediate that looks like this. And so there's a finite possibility, there's a measurable probability that your cell just lets go of this at this point. Right, all of this is just randomly happening, random things bumping into each other. Most of the time it stays attached. I think 99.99% of the time it stays attached. But that 0.01% of the time that it gets let go, you now have a free radical, or you have a peroxide in your body, which can turn into a free radical really easily. So this is why antioxidants are so important. If you're just breathing oxygen and living as a human or a mammal on Earth, you're constantly producing small amounts of peroxides in your body. This is why it doesn't matter how clean you live or what you eat or anything like that. If you live long enough, you will get cancer. Period. Because it's the number one carcinogen in the world, historically and still to this day, is oxygen. You can't go without oxygen, so what are you going to do? Get cancer.
And we all have cancer all the time. It's just our NK cells.
Right.
Good job. Yeah.
Yeah, so that's the other side to this too, is if you release free radicals and they're going around, if they happen to hit your DNA, it's one of the reasons why the electron transport chain is kept sequestered from most of your genetic material. Because it can't create a mutation in your DNA if it never runs into your DNA. But the problem is it just goes through an indefinite number of propagation steps in your body, unless you have mechanisms they call free radical scavengers. There's a whole class or pathway of molecules called that basically go around and pick up odd numbered electrons and cause them to react. And so that's all antioxidants are, is they're actually the vitamins and the minerals that support those free radical scavenger molecules. And usually it's some transition metal that has a 1 electron difference between two states. I think it's copper, because copper is stable as +2 or +1. And so if you have a copper that's a +2, it'll actually go, if it runs into a free radical, it'll steal an electron from that free radical to make it copper 1, and now you have an even number of electrons on your organic material again. And then if copper 1 is copper 1, if it runs into another free radical, it'll give away an electron to go back to being copper 2. But again, now you have an even number of electrons on your organic material. So basically, it's just an enzyme who holds on to a copper and then goes around and finds free radicals and holds them next to the copper until reaction happens, and then it lets them go. So free radicals actually are really good for you. It's not just health marketing, but there's not a reason you need a ton of them, but you do need to continue to support that process in your body, and it will actually, there's actually been a lot of research on effective peroxides on your skin elasticity. And a lot of physical aspects of aging are tied to peroxides, which is why smokers age so much faster, because smoking things is basically inhaling a whole bunch of free radicals when you're smoking things, and so you're making that mechanism in your body work harder, and it's not as effective. And living at altitude also ages people. Spending lots of time in direct sunlight also ages people faster, because you're producing more free radicals when you do that.
So for the record, what you're saying is that smoking is rad.
Yes, that's radical.
I was gonna ask, how well do radicals dissolve in water?
I mean, they're already pretty soluble as peroxides, generally speaking.
Oh, it's burn the radical
I mean,
flow to-
they're gonna be more, I guess, I don't know. They're not super stable as a gas, but they're also not super stable, period.
Yeah. The difference that I'm looking at is smoking a cigarette or smoking like tobacco.
A tobacco. So in general, the cooler, so that it's.
Because they're
By
not safe.
keeping it from burning as hot, the higher temperatures are actually what cause most of the free radical production. So by doing, so like vaping has its own health effects we're still figuring out. Especially as when it comes to like small particles in the lungs, gum stuff up. But in terms of the free radicals that you're exposing your body to, it would be noticeably less. I'm not sure how, I guess just by bringing the free radicals through a liquid and giving them a chance to react and stay stuck in the liquid phase, you might. I don't know if it actually measurably lowers the amount of free radicals or if it's just less harsh on your lungs just because it's not as hot. So something to Google. All right, well, yeah.
Back on the mechanism, with the
Mhm.
coupling step, why is the oxygen molecule single bonded there? Is that like an unlikely resonance state or?
Yeah, I think I would probably,
Formal charge of -1, right?
no, so this is not a formal charge of -1 because it's really just a resonance structure of O2.
Yeah.
Because you can see, you could draw that
Okay,
to get this.
yeah.
I would have actually drawn this step by starting from O2 to do that. But technically, that is a resonance structure of this, it's just not a significant contributor.
Right.
But this, if you run into a radical, instead of drawing like that,
Oh. Yeah, that makes a lot.
They just- yeah, I don't like that either. There's a few things in this book, the mechanism is very clearly laid out, which I like, but there's some of them I don't. For various reasons. Right, so the whole point of this slide is basically don't expose things that have, if there's molecules that you care about, don't expose them to oxygen if you don't need to. This is why Ziploc bags help keep food longer. This is why medication is packaged with inert gas. This is why you should also grind your own spices when you're using them instead of buying them pre-ground, because when they're pre-ground, you're basically exposing all of the inside to oxygen every time you open it. But if they're not ground up, there's the inside of the spices isn't being exposed to air, just the surfaces. So if you take it and you grind it up and you use it right away, it's gonna have much better flavor because none of this has happened to the bulk of the spice. The bulk of the plant cells are not exposed to air then. I thought so.
What about, like, putting nitrogen in these tires? Is that a molecule you're trying to prevent from oxidization, or is that just a stamp?
I'd have to look at it. Nitrogen's smaller than oxygen. You might maintain, so exposure to oxygen is one of the main reasons that a lot of polymers lose their elasticity. So you might actually preserve the life of your tire on the inside,
Not the outside.
but you're not gonna do anything about the outside.
That might be good if you don't drive a lot, right? Well, so, but then still crack on the outside.
Always had that question, it's like, why nitrogen? I guess that would be preserving the inside of the tire.
So a lot of times what you see is larger gases get used. If you don't want to have to reinflate it constantly, if you used something like argon,
Yeah.
that's a much larger molecular weight. So, or a xenon would be even better, but argon's got a molecular weight of 40 compared to O2, which is gonna have a molecular weight of 32, or nitrogen is 28. The larger molecular weight means it doesn't move through the polymer as fast. Basically, it's gonna stay inflated longer. Same reason that a helium balloon loses its size a lot faster than a balloon that you blow up by mouth. Because you're filling it with CO2 and oxygen and nitrogen instead of helium, which is tiny. The helium moves through that membrane really quickly. So you can make the argument that if you filled your tires with argon instead of just atmospheric gas, then they'll stay inflated longer. They'll keep that pressure longer. But I don't think it's about necessarily preserving the rubber so much because you can't do anything about the outside. I guess if you coat the outside really well with something, but
That's the tire shine or whatever.
could be, yeah. All right,
So I've been told before, like, it's the bigger molecules make a bigger cushion, which is what I thought.
well, I mean,